Hello once again, AP Calculus BC students. We are still talking about Taylor and Maclaurin series and Larson's 9th chapter in his 9th edition, section 9.10 in fact. Example 3 asks us to find a Maclaurin series for f of x equaling the sine of x squared. And this is a very popular kind of AP exam question. In fact, at the time of this recording, on the last AP exam, 2011's BC test, there was a problem somewhat similar to this. And the thing that I must emphasize more than anything else is that the intention on a problem like this is definitely not for you to build this from scratch. Think about that. Think about how much fun it would be to take several derivatives of the sine of x squared, right? The first derivative, well, maybe that's not so bad. You would have the cosine of x squared multiplied by 2x, right, to complete your chain rule. But from that point on, you're going to have product rules, right? So we're just going to say taking derivatives of f of x is too messy. Okay, so what do we do instead? Well, we have to rely on some common knowledge. Now that's the trade-off. If you don't want to take these derivatives, you've got to replace something with that. And that something that I'm talking about is recalling what your Taylor series, or Maclaurin series in this case, would be for f of x equaling sine of x. And if you recall, f of x equaling the sine of x is equivalent to, if you write it out term by term, it looks something like this. It is an alternating series, if you remember, containing lots of odd things, right? Which is exactly why the sine of x is considered to be an odd function. And if you write it in summation notation, it looks like this. Negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. Okay. Now, let's suppose that a student goes into a problem like this and perhaps, oh, doggone it, I forgot this item here. I forgot what the power series for sine is. That would not take very long to develop. Okay, that could probably be whipped out in, I'd say, in less than a minute easily. Okay, let's get rid of my little recording window here and then figure out a way that we can find the answer to our problem. What is f of x? And I feel very bad about my notation here. I should not say f of x is sine of x and then all of a sudden say, oh, f of x is sine x squared. That's just bad mathematics. So I'm going to put a little subscript up there, f1, for my sine of x. And then this will just be plain old f, sine x squared. Well, if you recall from a previous section in the Larson textbook or any other textbook that you might use, is that you can insert, you can replace values, right? Basically, this f of x is nothing more than f1 of x squared. Think about that. You're replacing the x with x squared. So that means you can go into your expression and replace any x value you see with an x squared. And I'm going to go ahead and do this both via the term-by-term approach and the actual summation expression approach at the end. So if you replace each of these x's with an x squared, you would be left with x squared minus, now what is x squared to the third power? We're dealing with this term right here. X squared cubed would be x to the 6th, right? You're going to go ahead and do your power to power, your multiplication. The denominator will stay the same. The next term, x squared to the 5th, is x to the 10th. Denominator stays the same. X squared to the 7th, yep, you guessed it, x to the 14th. The denominator stays the same. And it's really important that I do put these dots to indicate that this series will continue forever, because after all, I did put an equal sign right there. Now, if we want to rewrite this in more of a power series format, well, it's actually even easier. You would just simply dive into your power series and replace x with x squared. Well, what do we have here? If we take x squared that we've got right over here and then raise that to a further 2n plus 1 power, the laws of exponents say that we would distribute or multiply, and we would have 4n plus 2 as our new exponent. And then, of course, the denominator is going to stay the same. All right, so really, either of these two answers would be acceptable. Quite honestly, I do think I like the latter. I like this second one because it's a little bit more inclusive. However, the AP exam most often will ask you for the first few X number of non-zero terms. So you can stop there. Now, you really do need to address, or at least think about momentarily, what the interval of convergence would be for this guy. And luckily, it's not very difficult for this particular problem, because if you recall back, we learned that whatever the interval of convergence was for your original function, which in this case is f1 of x, well, we know that the interval of convergence for f1 of x is everything. It's one of the few series, Taylor series, that we discussed that is convergent everywhere. Well, if you were to manipulate that function, right, we called our f of x f1 squared. If we manipulate that, then what does that say about the interval of convergence? Well, it's going to be the same except for possibly at, class, the endpoints, exactly. So, what do you think about that? Should we check the endpoints of infinity and negative infinity? Well, that's sort of impossible, isn't it? It really doesn't have endpoints. So it turns out that the interval of convergence for your sine of x squared is going to be the exact same as your sine of x. And you could, if you had the graphing technology, you could easily throw this summation expression into your grapher. I would probably advise you to go a little easy on the infinity here so that you won't stall out your calculator, but pick something somewhat reasonable, say a number in the teens or 20s, and you'll find out that your curve will be very resembling of the sine of x squared. So there you go. There is your Maclaurin series for f of x equals sine of x squared. I'll see you next time.